Hi, everyone. My name is Takuhiro Kaneko from NTT Corporation. I'd like to talk about our work titled Improving Physics-Augmented Continuum Neural Radiance Field-Based Geometry-Agnostic System Identification with Lagrangian Particle Optimization. This study addresses geometry-agnostic system identification. As shown here, given multi-view videos, the goal is to identify the geometry and physical properties of the object under the assumption that the object obeys the conservation laws of continuum mechanics. In particular, we'd like to solve this problem without any assumptions on geometry and topology to broaden the scope of application. A representative previous study of this task is PAC-NERF. It solves this task by combining voxel NERF and particle-based physical simulation. More concretely, the geometry is first optimized statically using voxel NERF, then physical properties are optimized dynamically using particle-based physical simulation. However, a limitation of PAC-NERF is that its performance is sensitive to geometry learning done statically in a world grid space using only the first frame. For example, in sparse-view settings, it is often difficult to statically learn geometry. This failure adversely affects the performance of geometry estimation and physical identification in successive frames. To alleviate this problem, we propose Lagrangian Particle Optimization, LPO. This corrects the geometry by dynamically optimizing it in a material particle space using all frames. This allows us to correct geometry estimation and physical identification in successive frames. Let me explain the method. This study focuses on continuum materials that obey the conservation laws of continuum mechanics. Two notable points are that these equations can be solved using the differentiable material point method, diffMPM, and are applicable to various materials, including fluids, elasticities, plasticines, and sands. When correcting geometry with LPO, two standard PAC-NERF processes are first performed to obtain good initial conditions. The first is Eulerian static voxel grid optimization. This statistically optimizes the geometry in a world grid space using only the first frame. The second is physical property optimization. This dynamically optimizes the physical properties in a material particle space using all frames. The third is the proposed Lagrangian Particle Optimization, LPO. This dynamically optimizes the geometry in a material particle space using all frames. Since the diffMPM imposes physical constraints in a material space, the geometry can be optimized within the physical constraints. Furthermore, iterative geometry physics optimization is introduced to improve the geometry and physical identification iteratively. In this optimization, geometry optimization and physical property optimization are alternately repeated times to find the optimal states iteratively. Let me discuss the experimental results. The effectiveness of LPO was evaluated on the PAC-NERF dataset, which consists of 9 scenes, including 2 Newtonian fluids, 2 non-Newtonian fluids, 2 elasticities, 2 plasticines, and 1 sand. In each scene, the objects fall freely under the influence of gravity and undergo collisions. 3 views were used for training, and the rest were used for testing to simulate sparse-view settings. PAC-NERF 3V, PAC-NERF trained with 3 views, and PAC-NERF 3V DAG, an improved variant for sparse view settings, were used as baselines. These are the results for the torus scene. In the third figure from the left, PSNR is improved by correcting the geometry using LPO. In the rightmost figure, PSNR and physical properties are improved by applying the iterative geometry physics optimization. These are the results for the cream scene. The same things can be said for this scene. In the third figure from the left, PSNR is improved by correcting the geometry using LPO. In the rightmost figure, PSNR and physical properties are improved by applying the iterative geometry physics optimization. Quantitative evaluations of geometric correction show that LPO improves PSNR, SSAM, and LPIPS. Quantitative evaluations of physical identification show that LPO improves physical identification in most cases. I'd like to conclude the presentation. To improve geometry-agnostic system identification, we proposed LPO and iterative geometry physics optimization. The results demonstrate that LPO improves system identification in sparse-view settings. The simplicity of LPO facilitates its application to various physics-informed models. Thank you for listening.